Okay, let's probably start.
Where is the right spot?
Okay. Have our NIA CFD seminar. I already forgot what the number is, like 127. Okay. Yeah, and our kind of guest today is Beckett Zhou. We used to have him as an NIA researcher for a long time, so that it doesn't feel like that he's guest, but this time he's visiting us from University of Bristol in UK, and there are several people coming with him who collaborate with Beckett. The topic of presentation today is Propeller aeroacoustic research at the University of Bristol, and Beckett will present models for aeroacoustics of various fidelities and complexities. And please take over, and thank you for visiting us.
Thank you, Boris, for the introduction. And yeah, it's welcome. It's nice to be back, and thanks everyone for attending. So today I would like to share with you guys some of the recent efforts on our team on the Propeller aeroacoustics research, mostly on the numerical side, namely simulation, optimization, data-driven methods, and also some synergy with the experiment. And I'm also pleased to have my experimental colleague from Bristol, Nick-san. So some motivation, real quick. So why are we doing Propeller aeroacoustics research? Well, with the emergence of UAM, eVTOL type of concepts, we are entering a new era of aviation, and noise, as we know, is identified as a leading source of concern of UAM, eVTOL by EASA and FAA on societal acceptability. And the detrimental effects of noise on health is very well documented. So there are many noise sources coming out of UAM, DEP type of configurations, and out of all these, propeller noise is by far a dominant one. So we would like to to work on it to try and understand the fundamental mechanisms and also try to reduce it. So I begin with some challenges. Firstly, these propellers, these days they are becoming smaller. They are rotating at much lower tip velocity than the conventional turboprops. But because of that, the relative importance of broadband contribution is now elevated. And this then contains certain key features that must be captured. And for example, laminar separation bubble, transition, reattachment, and so on. So usually for these things, we need the scale resolving simulations to be able to capture a full range of noise spectrum. And then to do that, we use typically scale resolving methods like LBM, LES, and so on, and also experiments. But these are much too expensive, and they do not meet the time to solution requirement in the industrial context. On the other hand, if we resort to low fidelity methods like play element momentum theory, status type of methods, and so on, they can be very unreliable for off-design conditions, and they're not able to capture the broadband range without significant modifications. Another challenge is the interaction effect, so insulation effect. So the strong airframe propeller airframe interaction, and because the propellers are now mounted so close to the airframe and also close to each other, this also intensifies the acoustic scattering effects. And so all these must be captured, and numerical tools must be adapted to and improved to to meet these new design requirements. So in this talk, I'll share with you guys some of our recent efforts in meeting some of these challenges. The first part is a low-fidelity framework for rapid prediction and the optimization of propellers. Then this allows us to look at the aeroacoustic and aerodynamic performance. And on the acoustic side, we look at both tonal and the broadband parts of the noise. And to enhance the broadband prediction, we use a machine learning method. We applied machine learning method on the trailing edge noise model, which I'll explain in a bit more detail. And then moving on, we're going to jump to the high fidelity end, talk about hi-fi LES simulation for propeller to trying to capture the broadband noise range. And thirdly, tying it reconciling the two levels of fidelity. We will present a multi-fidelity data-driven framework to enhance noise prediction using transfer learning and active learning. And I'll close by also highlighting some other recent ongoing developments as well. So now I come to the first part, which is an integrated framework for rapid prediction and optimization of propellers. So I will not have time to really go through this flow chart, but essentially this is a joint-based design optimization framework we have developed using a Python-based framework. It's called JAX, and the JAX XLA package compilation technique allows us to have GPU acceleration, and this enables us to have very rapid optimization of aeroacoustic and aerodynamic performance of isolated propellers. The adjoint is computed using the autograd capability of JAX. This code is very fast, so in terms of time to solution, it takes really minutes to construct the entire Pareto front when you have multi-objective problems. And the key, also another key to this framework is that we are able to not just optimize the planform distribution of propellers, which is typically done, but we also allow the blade sectional shape to be optimized, and I'll show later why this is very critical. So the first element of this framework, which is basically the primal part, the forward part up here, it's basically built around the blade element momentum theory solver, and it relies on the 2D sectional force data from airfoil, and we use frontal loss tip loss factor to try and model the 3D effects. Okay, so that's this part of the flowchart, and then that will give us the torque and thrust. And in terms of the tonal SPL, we use the Hansen propeller model, and this is a frequency domain model, and it accounts for the span-wise variation of loading on noise, and it basically takes the sectional torque and thrust from the BMP solver. So we performed some validation, and this is what we have so far. So and this is performed on a two-bladed TU Delft propeller.
Because we used to ask questions in the middle.
Oh, okay, sure. Sure, please.
We'll use this feature. So this is basically actuator-based model, right? So that so you capable to predict noise from this, because I thought that this is a kind of typically was the main disadvantage of the actuator-based model. So that the noise is predicted by using different model, right? So it's
so the noise is computed using the so-called Hansen model. So BMT will give you the sectional loads, and the sectional loads you provide to the Hansen model to compute the noise, because the tonal noise is basically driven by the load distribution.
Okay, so that's kind of the two things.
Yeah.
together. Because we try to think how to generate noise from actuator model, and so that basically what we are saying, we are just missing some additional model.
Oh, you can easily generate noise from actuator. If you have the loads on the propeller, you can generate noise, but it's you will be capturing a part of the noise, right? With steady loading, more or less. If you have unsteady loading, it's actually this standard actuator. This method will also not work. Also, we will not capture the broadband part.
Okay.
Yeah.
Okay. But the blade element, that'll pick up the change in angle of attack.
Should I rejoin or?
I hear.
Okay, now I think we can get an echo.
It doesn't have to be on axial flow. If you have like a rotorcraft, they do that, break the noise from a line that's on the blade. That could be edgewise flight, which is very dependent, so it doesn't have to be axial flow. As long as you model loads on the blade as a function of time, aka azimuth, you can break the noise.
Right.
I'm not familiar with Kansas frequency domain, but everyone can get.
Right, but I think so. I think the standard. I think we're back.
I don't know about Broadband.
It seems that we're back.
We heard voices from your machine and the music.
Okay.
Okay, folks online, sorry for the interruption, sorry for the technical difficulties. But yeah, Mike, to answer your question, I think the standard BMT method assumes you have axial flow, so the angle of attack is 0. I'm aware that there are modified methods that will take care of non-zero angle of attack. But yeah, basically what this does, so this is actually not entirely accurate. There's actually a loop in between these. So you have the sectional load, and then you have to compute the induced angle of attack, and then you iterate until you.
And if you have, for example, actuation, you can
that, but also these, right? It's different, right? As it's rotating around.
Okay. Sorry.
So go back to the previous slide with the flow chart.
Yeah.
I see things like DT, and I'm assuming there's thrust, DQ, and DSPL with DX prime or I. That's the design variable. I think that looks like a forward derivative. Are you doing forward derivatives or backward derivatives?
Well, this is based on the design sensitivity it's evaluated in the reverse mode.
But it's all going that way. Okay. I don't see where it's reversed. Because reversed, you wouldn't get how the thrust changes with respect to the design variable. You'd get how the objective function changes with everything. That's it. You do that, backwards. So
well, okay, but so looking at this, right? So if you differentiate with T or Q with respect to the design variable, you'll get DT dQ. Yeah, and then if you compute the reverse mode, of this path, you'll get the sensitivity, and you can do the same. But obviously, if you want to DT dx and then DT SPL dx, you need to compute it. You need to compute the adjoint or the reverse mode twice, right?
yeah, where your objective is then SPL or
Yeah.
So is that what you're doing in the previous chart? You're saying these are different executions of the same thing?
These are different. Yeah. These are different.
Right, so each of those represents a unique execution of the line.
Yeah. So you're not. Yeah. So these are not forward derivatives. Yeah.
Okay, I understand.
Or almost. Okay. All right. Let me continue. So validation is done on a two-bladed propeller from benchmark from our colleagues Team Delft, and yeah, you can see the load in terms of load prediction, torque and thrust are predicted reasonably well. for such a lo-fi method, it's actually not much worse than the Ryan-based approach. And in terms of the tonal SPL, the shape of the spectrum is captured quite well. There is a shift. The maximum deviation is about 2 dB. That's pretty much the best we can get out of such a lo-fi type of methods. And now for this approach, we would like to get to do design optimization. So we need a sensitivity, and to do that, we use algorithmic differentiation, which we apply to we would like to apply to the whole chain like this. It would have been easy if we didn't have to differentiate to aerofoil. So what we did to circumvent this problem is that we replaced this part, the sectional, the aerofoil part, with a deep neural network, which gives us the backward, so the derivative as well. And we train it with 5 different inputs. So things like camber position, thickness, angle of attack, timbre, and so on, and gives us the 2-dimensional lift and drag coefficient. And this is on the top right corner. This is just to show that the neural network prediction is pretty much the same as the direct aerofoil prediction. So you're not losing much information. And added advantage of this is that once the neural network is trained, once you're in the online phase, it's several times faster than coding aerofoil each time, especially considering that in this part, there's quite a bit of iteration between the two. So you are actually saving a bit of time, in addition to being able to compute the sensitivity. So we apply this to the optimization of efficiency optimization of a 2-bladed propeller with both thrust and tonal noise constraints. Okay, so the thrust constraint at its baseline level, and what we do is we progressively vary the tonal noise constraint. Okay, so from let's say 62, 63 dB down to 59 dB, and by doing so, we're able to generate a Pareto front. And we generate 2 Pareto fronts, the red one is if you only optimize the platform distribution. The blue one is if you optimize both the platform and the sectional shape. And by sectional shape, I mean for each section, the profile is allowed to be completely different. And you see the importance of allowing the sectional shape to change. You see that the blue lines over the entire range of SPL is sitting on top of the red line. This means that you are able to, in general, achieve better design with the same constraint. And especially when you have more stringent constraints, and this is even more important, when we saw that when the SPL constraint goes below 59, the platform only optimization is not able to achieve an optimized design anymore, but it's not able to meet the design constraint anymore. Okay, so that is the tonal part. We've done the tonal SPL optimization. So the next question is, what about the broadband part? How do you say important? So the broadband part is very important in many cases, and this is actually coming out from our experiment, right? So we actually manufactured 2 propellers with 2 different cross-sectional airfoil shapes, and you see that for one of the propellers, the broadband range is really highly elevated. So which definitely in the design we should try to take that into account. To do so, we use the so-called ambient trailing edge noise model, and I've thrown out the equation up here. So the core of this model.
Sorry, for the previous one, you're looking at those 2 different airfoils. Did you sort of optimize so that they have the same performance? Because I guess the one's got camber, so it's going to have more lift for the same conditions. So is it sort of changing the airfoil with the same propeller shape, or is it optimizing given those sections?
It's next group.
The next.
Oh, this one.
This
No, but this is not an optimization. This is just this is just to show that the broadband part is important. This has nothing to do with optimization.
Okay, and
This is
they're both
actually an experimental
generating the
test.
same thrust?
Sorry?
Are they both generating the same thrust?
I think relatively close because they operating operated at the same RPM and it's also at the same pitch diameter ratio.
Okay.
Okay, one is camber and one is not, so they will have different thrust.
Okay.
Yeah.
Okay, thank you.
But you gotta be very careful here because you have the same thrust, but what torque? Your constraint is thrust, not CQ over sigma.
Yeah, but this is not optimization.
You need to go back. Go back. Your constraint there is thrust.
Correct.
What's your torque? Right? Are you using more power to generate less noise? You don't know that. So your constraint should really be CQ over sigma. And I made the same mistake in my paper. I only did thrust constraint.
Yeah. Okay, but we take into account the torque part in the efficiency.
Yeah, but
Right.
that's true. And I use the argument too. So I'm maximizing efficiency. So essentially that's CQ versus Q. But I think, and Doug is trying to hammer this into my head, Doug Boyd, is that you can have efficiency, you can have thrust, but if you don't match CQ over sigma, are you really comparing apples to apples?
Yeah, but okay, again, if you are constraining your thrust and you are trying to optimize, you're trying to maximize your efficiency, effectively you are reducing your torque, the torque required.
That's something I haven't gone through yet, and I think we should go through that.
But you did raise an important point because I think torque on its own has to be constrained because otherwise you need a different motor.
Yeah.
What is sigma?
Solidity. It's the area.
Is it constant here or?
Area of the blade over the disc area.
Oh,
So
the area will change.
Because chords go way down.
Yeah.
Right?
Okay. Yeah,
It's a function of omega, right? Because your coefficient. So it's something that I haven't looked at yet either. I did something very similar to what you did, where I just did thrust, and Doug yelled at me to do CQ over sigma. So that's something I think that we both should look into.
Right. Okay.
So it should be some constraint on some area.
Yes. Yes.
Yeah.
Okay. Right. Okay, so moving on. So for the broadband part, we model it with ambient model, and in the core of this is a work pressure spectrum model by PP. And in our code, we have implemented different WPS models like the Rosenberg 2012, Schlenker TNO model, and so on. And most of these models require some boundary layer characteristics, which we compute again from aerofoil. And once the sectional sound noise is computed, we essentially integrate it over the propeller and make it spin using the rotating blade formulation from Pagano. And this approach is pretty well established, pretty well known in the community. So I'm not going to get into too much detail. And this is just a validation of sound pressure level for a fixed airfoil. I'll show a comparison for rotating blade later, which is not so trivial. So following this new red branch that allows us to model at least the broadband SPL. Again, we want to do design optimization, so we need to essentially if you remember the DNN from before, we have to retrain the DNN by including additional boundary layer input as boundary layer output. Sorry, in addition to the CL and sectional CL and CD, and we in this case we also allow the airflow to be parameterized with nervous control points to enable more general shape deformation. So now stitching this together with the BMT, with the broadband noise model sensitivity, we are able to then compute a coupled adjoint of broadband noise component with respect to these nerves control point, but we also retain the option to differentiate that with respect to the more standard design parameters like the camber thickness, locational maximum camber, and so on. And adjoint sensitivity is validated against finite difference, as you can see here. So the error for the most part is.
So you have alternative way to parameterize airfoil using this camber thickness, not just nerves.
Correct. Yeah.
One more question.
Yes.
Same airfoil throughout the whole blade, or is it a function of span?
So it's a function of span. So at different span-wise locations, you are allowed to have a different airfoil. Yeah. And so the one point I forgot to mention is that the chord and the pitch distribution of the airfoil is also a design variable, and they're actually also parameterized with Bezier curve, so that you ensure that you don't have one blade that's like this and then the next blade like this. So yeah. Right, so sensitivity is validated for the most part. Error is 10,000%, so we can reliably use that for design optimization. Before we do that, this allows us to just look at the sensitivity. So what is how does the broadband sensitivity behave with respect to key design parameters like pitch, camber, chord, and thickness at different sections. So what I'm plotting here is a sensitivity color map. So in the horizontal axis you have the frequency, and then the vertical axis you have the span-wise position of the section. We are only plotting here the above 70% chord. And this is based on a two-bladed propeller operating at 5,000 RPM with 15 meters per second inflow. What you can see directly from these figures are two trends. The first trend is that when you increase the pitch, the camber, and thickness, this leads to the lower frequency of the spectrum to increase strongly, and at the same time reduces the higher frequency component. This is because doing so, increasing these pitch, camber, and the thickness increased also the turbulent length scale of the turbulent boundary at the trailing edge. So it has this kind of effects, and this is consistent with the broadband measurement performed on fixed airfoil by Hutchison and Brooks. The second trend is that by far the dominant broadband noise sources are located in the tip region, as you can as revealed by the sensitivity magnitude, and this is also consistent with LVM-based numerical beamforming performed by Damiano Casalino's folks using power flow, and it's also consistent with our own LES simulation, which I'll show later. So now we go ahead and do a design optimization for broadband. We do a thrust-constrained noise minimization, targeting the broadband noise between 1 kilohertz and 10 kilohertz. So the objective function is essentially just a weighted average of the SPL in this frequency range. Here I'm comparing the sectional shape at different span-wise locations, and what you see is that the optimizer basically shifts the load inward, and then it maintains the thrust constraint by increasing the camber and pitch in the inward sections. Okay, so it does that to compensate for the thrust. In terms of tonal broadband SPL, here we're comparing baseline and optimize at three different frequencies. So the red one is 1 kilohertz, and then you have the blue one 5 kilohertz, and then the green one 10 kilohertz. So in all frequency, every direction, the broadband noise is reduced. On average, it's about 3.3 dB reduction over the frequency. Interestingly, even though we did not directly target the tonal noise, the tone is also reduced. in some directions up to 3 dB, and we got that for free because what the optimizer did was that it basically shifts the load inboard. So and we know that the load near the tip region is very strongly contributing to the tone, more so than the inboard section. Yes.
Did you put any constraint on the cord at the root? Because things got attached to the hub.
Yeah, for this study, we did it in a quote unquote crude way, where we start only the optimization only at the, I think here we're showing the 40% chord. We actually started at something like 30% chord, but we did not enforce some sort of continuity or some sort of C1 continuity between them. That's something that we need to do. Yes. That's an important point. Now, looking at the Pareto front, that also reveals some very interesting information. So, what we are seeing here is that so at this point you have the 100% of the thrust. So you don't sacrifice the thrust, and the noise reduction of the broadband noise reduction is about 3.3 dB. But what you see is that if you are willing to relax the constraint, by just 2.5%, if you are willing to lose 2.5% of the thrust, you get much more noise reduction up to like 5 dB. So that's really important information to have for designers. And this whole framework we presented at Aviation the past week. So if you're interested, please have a look at it. That was the first part of this talk. So we were able to do propeller optimization for tonal noise and the broadband noise. So so mission accomplished and so done. It's actually not so simple because we rely for the broadband part we rely on ambient-based model, which relies in turn on wall pressure spectrum. And it turns out that these trailing edge noise models or wall pressure spectrum models, they are not so reliable. They are not so robust at all. So here are two figures that I borrowed from our colleagues from TU Delft for their benchmark propeller. So the purple is the experiment, and with two bladed propeller operating at 5,000 RPM, and at here we're showing two different flow conditions. Flight speeds. You see, and we're comparing different noise models, that's not with WPS models. So you see that in a static condition, for the most part, most of the models are at least able to capture the trend reasonably well. But as soon as you go up to, you give it an inflow velocity, go up to 10 meters per second, everything goes haywire. So what this is telling us is that the existing noise models, broadband noise models, are really not accurate or robust enough for propeller broadband noise prediction at different operating conditions. So, and why is that? For the most part, the reason is that the accuracy of the prediction strongly depends on the underlying WPS model, which is this 5 pp term. And most of these WPS models are empirical or semi-empirical in nature, and they are calibrated to certain types of flow. So, for example, the Rosenberg 2012 model, which is quite well known, used by a lot of people. It tends to perform really well when you have very strong atlas pressure gradient, like for example in this case. But in the case of mild pressure gradient, the performance significantly degrades, and then you have a high frequency roll-off, very significant roll-off in this case. So what we are trying to do now in this in our work is trying to set up adaptive WPS model parameters using machine learning, so that the model can respond to the actual flow conditions, and not being calibrated to or tied to a certain type of flow. We actually applied this framework to different WPS models. here I'm only showing one. I'm only showing the Rosenberg model, the application to the Rosenberg model. So won't go into detail of the model because if you were to show the equations of this model, it takes a couple of pages. But basically, we selected 5 different most influential parameters in this model, and we want to tune these. What we do is we use an adjoint-based inverse design approach for each training sample. So effectively, we look for the optimal model parameters, these 5 optimal parameters, by minimizing the discrepancy between the model prediction and the experimental data. Okay, and obviously to achieve that, we solve essentially it's an inverse design problem for to match the two. So the flow chart here is basically showing what I just said. You solve an inverse design. So for each sample you get you solve for the optimal tuning parameters. So how many samples do we have? So for this we rely on experimental data measured in our own wind tunnel for different airfoils. So we looked at 4 different airfoils, and we perform the test at different flow conditions. So 2 different velocities mostly, and different angles of attack, which will generate different profile boundary layer shape characteristics. And we perform the measurement of work pressure spectra at different trailing edge locations. So if we repeat this approach for each of these samples, we'll have a number of input and output pairs, and we can then train a neural network. So and then in the online phase, given the boundary layer characteristics, we would interrogate the DNN to give us the optimal WPS for the model. So and then we use the update the machine learning enhanced Rosenberg model to compute the farfield noise. We tested against different samples. So here we're looking at so-called V2 airfoil, which is a highly cambered airfoil used in automotive fan, and then we have this the well-known NACA 5-digit airfoil. So the top row, so these 3 columns are different WPS models. So we looked at Rosenberg, Schlinker, and TNO models, and then the 2 different rows are the 2 different airfoils. So we see that for most cases, we are able to achieve very significant improvement of prediction using the machine learning enhanced WPS model. Now we take that and we put that into Propeller noise code. Okay, and we can see. Let's focus on the forward flight cases. So the non-zero advance ratio cases. So the red lines are the standard unenhanced noise prediction using the standard Schlinker WPS model, and the green one is the enhanced prediction. Okay, so we are indeed able to strongly improve the broadband noise prediction for these cases, except for the static condition. And this is actually due to the fact that you have pretty strong separation and the stall noise component that's not really captured for these conditions. Also, we published this work at Aviation last week. So if you're interested, please have a look at this paper by my student Aurelia and Nicolino. The next challenge we face, and this is something that we're going to work on hopefully in the summer, is to target the stall noise component. So, and this is quite important in propellers, where certain sections of the propeller at different flow conditions are actually stalled. And when you are operating in stall condition, these WPS models are not valid anymore. In fact, they don't have the right functional form to achieve the correct shape of the spectrum. So we need to open up the functional shape and allow the machine learning model to get there. Okay, that's one thing we need to do. And the other thing, actually, and let me just go all the way back, is install, we also need to look at the length scale and also the transfer function, because when you are in the stall condition, these models. Okay, so still quite a bit of work to be done to make it a bit more robust and more reliable. Okay, so here we've used experimental data to do to help us do the enhancement, to do the training and so on. Another source of high fidelity data is obviously using LES. Okay, and this is what we are also doing. And this is a two-bladed propeller, 9x9 propeller manufactured by our industrial partner Meslik, and this was actually tested in our wind tunnel facility for both load and noise. And for simulation, we performed at two different velocities. So first one is static condition, so the hover. The other one is forward flight, so with an advanced ratio of 0.66. For simulation, we used SU2. We used the well-resolved LES in SU2, and we coupled this with solid surface Fox-Williams-Hawkins acoustic analogy in F1A formulation. We've got three different grid resolutions. So far, we've completed the simulation for the medium and the coarse level. So the medium level is about 250 million cells. We are almost done with a fine grid, which is 500 million cells. These simulations are computed on the UK national cluster Archer 2, and one of these simulations from beginning to end takes about 1 million core hours. So quite hefty computation. So first, let's look at the surface flow characteristics. So here we are extracting the velocity, the vorticity at different span-wise locations. And you see that in the Hubbard case, the flow is largely separated at leading edge, directly from the leading edge, and over here, and we are plotting the wall shear stress. Okay, so the flow is separated. There's not much reattachment. On the other hand, for the forward flight case, it's quite different. It's quite interesting. You've got flow is attached in the first more or less 40% chord, and then you have a laminar separation bubble, which is here, across a large portion of the span, and then you have reattachment, turbulent reattachment here, and this is actually quite consistent with TU Delft findings, which they for study they perform on a very similar propeller using oil flow, which I showed here, and also displacement simulation. Okay. So now moving on, it's useful to compare the performance between runs and the LES. So here we're comparing. Let's look at the first column, the surface pressure. So top one is runs. So runs in rotating reference frame. If you compare that with time average LES simulation, it actually compares quite well, except for the fine features in the trailing edge. But for the large part, the mean pressure actually compares quite well with high fidelity LES. This explains why, and by the way, this is forward flight. This explains why often when you use run simulation, you are able to capture the tone quite well, because the tone basically comes from unless you have strong separation, the tone comes from the steady pressure distribution being spun around by the propeller. However, if you compare that with instantaneous LES, you see that the high frequency fluctuation in the trailing edge is missing. So that also explains why with runs you cannot capture the broadband noise at all. Right. So now if you compare the wall shear stress for LES, so this is the time average the LES, and again we see a laminar separation bubble. Of course, a pretty large portion of the blade, and you have turbulent reattachment. Runs, on the other hand, it completely mispredicts the wall shear stress, and this leads to strongly delayed separation. due to the so we're not using a transition model, and there's no reattachment at all. Okay, and this is actually the fact that it has no reattachment.
The grids were comparable, right? For rounds and LAS here, this computation grid size was comparable.
We're actually using the same grid. Yeah. So it's not so the
it's not a grid.
It's not cannot be
that's average.
Yeah.
Because of eddy viscosity, not
right.
because of
it's entirely because of data. Yeah. Right. So the fact that RAS it does not give you reattachment when it needs, because if you were to consider coupling RANs with let's say a synthetic turbulence model to try to capture the broadband, it will still give you the wrong solution because it has no reattachment here. So the broadband source that you synthesize is still going to be completely wrong. Okay? But nevertheless, let's go back to the LES simulation. So here we're looking at the hover case, comparing with experimental data, and we see that and we are comparing at 3 different polar angles. The tonal level is underpredicted by 3 to 5 dB. The broadband level in general between 2 and 10 kilohertz also underpredicted. So the hover case is actually quite challenging to simulate because in hover you have very strong plate loading. Okay, and these propellers in test they flex, and so the aeroelastic effect is not captured by LES. In LES we use a rigid blade assumption. So there's a lot of basic physics or phenomena that's simply not captured. Okay, so that's part of the reason. But nevertheless, we see that the shape, general shape of the spectrum, and also and we also see that there's very little discernible difference between the G1 and G2 grid. This actually makes sense because the flow, if you remember, is for hover is over the blades highly separated. So it's massively separated. So when you have a massively separated case, it actually the resolution in the boundary there actually is not that important anymore. This is why when you have a coarser grid, it actually doesn't perform so bad compared to the. Now moving on to the forward flight case. So the same 3 polar angles, and we see that so in general the tones are better captured, but also the broadband noise range above 2,000 hertz is also very well captured by simulation. You will see that in the mid-frequency, low to mid-frequency range. So between the blade passing frequency and about 2,000 hertz, you've got a misalignment, you've got a mismatch, and we are under. And this is because the insulation effect and scattering of the propeller rig, and perhaps also of the tunnel wall nozzles, they are not properly captured by this isolated propeller LES. Yes, ma'am.
How the blade element method do compared to this?
Blade element?
Yeah, you did blade element on this, right? To design the blade.
You mean that the BMT coupled with ambient?
Yeah.
We have not actually checked this yet.
Okay.
Yeah. But we're actually doing it now. We actually so on the surface of the blade, you can with LES you can actually extract the LES resolved WPS, and you can actually stick that WPS into ambient, and that should
auto rounds, right? So that we use kind of synthetic turbo.
Yeah. Well, if you have the WPS, you can directly propagate it, or you can directly put it in the ambient model, which I showed in the previous section, and that will give you should in principle give you better prediction than ambient model that's relying on the WPS model.
For tonal noise, compared to the BPS.
Sure.
Are you capturing that?
Yeah.
Are you consistent between your blade element model and your LES? Yeah. You're not on the tonal level.
Yes, we actually for the tone we actually did compare both the BMT based method and also RANs, and they are good agreement with the LES. Yeah. Yes, Max.
Out of curiosity, at the very high end, it looks like the numerical broadband rates drops off compared to experimental
Well, I think in this range, maybe Nick can comment on this, but okay, I was going to say basically that so this part, right, is mostly motor noise. This is loaded motor noise, but whether I think above 10,000 hertz, the noise will drop off because start to drop off because of the grid resolution. But also in the experiment, I think you do have spurious noise anyway up here.
Probably not spurious noise, but flow noise. So towards high frequencies, it's normally very difficult to judge which one is more accurate. If you have a really good grid resolution, I usually intend to be a bit more.
And hover also, this is sort of like the previous slide. Hover, you're going to have all sorts of other noise sources that you're not modeling. Right?
So you're supposed to have a roll-off, but the roll-off, I mean, ideally it should follow some kind of roll-off of the training noise. That's dominant.
Yeah. Okay, so last point that I want to make about these slides, these figures, is that in this case we do see that G2 does outperform G1, so the medium grid does do a little bit better. It does not have this spurious high frequency hump, mid to high frequency hump that you see here in all three angles. Okay. Now this simulation does reveal very strong broadband noise source. Okay, in the trailing edge, above about 50% of the span due to the turbulent flow reattachment. It allows us to extract trailing edge WPS and also compute things like span-wise correlation. And these can be used to develop and tune propeller broadband noise models for industrial, for practical design purposes. And we also presented this work at Aviation last week. So if you're interested, please have a look. Currently, some current efforts, we are completing the work for the finest grid level. We are looking at higher advanced ratio, so achieving higher tip Mach number, because when you have a Mach number exceeding 0.3, 0.4, the quadrupole noise, so the volume noise source start to become significant, and this was shown not for propellers but for fixed blades. People have shown this, that volume source becomes a bit more important. Moving on to higher Reynolds number, we are also trying to model the LES, and also we have some upcoming experiments that will measure the wake development with PIV, and hopefully I can convince Nick to perform some oil flow visualization on the blade.
We already did that.
Yeah. But not forward. Forward is going to be challenging.
Yeah, we're going to do both.
Okay.
Yeah, sure.
It's as far as I know, it's a messy endeavor. Yeah. Right. Other ongoing work, we are looking at going from purely forward flight, axial flight to going towards edgewise flight, so increasing angle of attack, and some visualization that you see going from 0, 15 to 45, and here I'm about to show some movies. So again, angle of attack 0, 15, and 45 degrees. It's not coming out very clearly here, but you can see probably if you compare between 0 to 15 degree angle of attack, you see that two things. So one is that the unsteady loading magnitude outside of the broadband noise source zone has significantly increased. So this means that the tone will also increase due to the unsteady loading part. Okay, as soon as you have an angle of attack of at least 15 degrees, The other thing to notice is that the broadband noise source zone has been enlarged, so it got bigger. So this means that the broadband noise, we also expect that to increase. If you look at the 45-degree case, you see very massive separation on the suction side of the blade, and this actually is quite interesting because it reminds us of the behavior of hover case at 0 degree angle of attack. It's almost behave almost like civics in hover. Okay, so so that was with LES simulation. So now you got you can do the enrichment with experiment with you have some LES data. So the question is, how do you further enhance the level of fidelity? So I'm throwing up this slide, these figures again, so that to remind us that the challenge is to improve the accuracy and robustness, right, of the broadband noise prediction without excessive use of high fidelity data. And this is a very important point that I want to make, is that we don't want to just blindly throw lots of high fidelity simulation or experiment at it to train a machine learning model, because in the end that becomes a zero-sum game. If you have thrown so much data at the problem, then you are just doing a glorified curve fit. Okay, and that's not what we want to do. So the idea is that we want to go multi-fidelity. We want to use a machine learning model to optimally kind of infuse the low fidelity and high fidelity data. So so 3 ingredients. So we start with machine learning model using a large number of inexpensive but less accurate lo-fi simulations. Then we complement that with a small number of expensive but high fidelity samples, whether it's experiment or simulation. Then we blend the two with the so-called transfer learning approach to help us enhance the model. And I'll explain what we mean by that. We actually what I'm about to show later will be what we did for the broadband noise, but this is for the tonal noise prediction, which we showed in the previous year. So essentially same framework, but so for the lo-fi DNN, it's based on the BEMT method coupled with a very low fidelity Garrett-Watkins propeller noise model. This model does not even take into account the span-wise variation. So it's very, very low fidelity, both in aerodynamics and acoustics. And what we did was that we performed experiments on 18 propellers, 18 blades, measured at different RPM and flow velocities, and we did a transfer learning procedure on this. And then we followed that by an active learning algorithm, which is built around a Gaussian process regression model for the predictive error of DNN, in order to help us find additional experiments, identify additional experiments to be conducted to target the regions of the high discrepancy. So that was what we did more than a year ago, and that was the result. So this is the lo-fi prediction, and here we are showing the parity plot. So measured versus predicted. So if you have a perfect prediction, then everything will lie on the diagonal. And you see that the lo-fi model has pretty big spread in terms of its prediction. And then if you do transfer learning using these blades, you are able to reduce the mean squares error by almost half. Okay, and then you do one more round. We did one more round of active learning, and we are able to even further reduce the mean squares error. And this work was presented at the Aeroacoustics conference last year. So if you're interested, have a look at that version of the work. What was missing in that work is the broadband part. So now I'm going to show you what we did for the broadband part. So we start by defining the design space, so we can apply this to just any propeller. And this procedure is in the machine learning world is known as the input feature selection. To help us understand what's important, what's not, we again, these are preliminary experiments, and this was performed by Nick here, and we're looking at four propellers, so two different blade cross sections, and two different pitch to diameter ratio. And what you see is that if you look at the NACA 0012 profile, when you go from 0.8 pitch to diameter to 1.4, the broadband noise part has increased. On the other hand, for the 4412, the trend is the other way around. Okay, so what this tells us in a very general way is that both planform and the sectional shapes are important players in noise generation. So what we did was that we defined the first three of our design variables to reflect that. So we have maximum camber, location of maximum camber, thickness, and P over D ratio. So essentially, we're looking at a NACA 4-digit series, and we test them at different P over D and different operating conditions, and these are the bounds that we set. Okay, so essentially, it falls. Things like they will fall inside this box, but we also remove the speed and RPM pair to discard the windmilling ones. So because in some conditions the propeller will windmill. A couple of things are fixed. So we look at for this study only two bladed propellers, fixed diameter and fixed the chord and the tip geometry. The tip is just a flush cut, very simple flush cut tip. The next step is to train a lo-fi based DNN. So for the lo-fi, like I said, we showed before, we were using the AMIA based model, and here we're comparing two entirely different propellers at different operating conditions. And you see that the performance of the lo-fi prediction is highly dependent on the blade geometry and operating conditions. So in this one, on the left one is working pretty well, and once you change to a different propeller, different condition, it's not reliable anymore. The deviation is something like 20 dB almost, and even for the same propeller, if you just perturb the flow condition slightly, the SPL, the prediction also degrades. So, but nevertheless, that's the whole point of this work, is to try to enhance the lo-fi prediction. So what we did was that we generate 54,000 samples in this 6-dimensional design space of the lo-fi, and this gives us a lo-fi data set ELF. And we train a machine learning model, which is nothing other than solving an optimization problem against a loss function for the weights of the neural network. So as a reminder, we have 6 input features. In terms of output quantities of interest, we are looking at SPL at 3 different angles of attack, and for each angle, each polar angles, we are looking at frequency range between 1 to 7,000 hertz at 1,000 hertz intervals, so 7 points. So in total, we have 21, 3 times 7, 21 outputs. Okay, to assess the effectiveness or the accuracy of the neural network and have a prediction, we rely on experimental facilities at the University of Bristol. In Bristol, we are quite lucky to have currently fully functional 2 aeroacoustic wind tunnels for experimental studies, and this gives us allows us to have a state-of-the-art flow and noise measurement techniques like hot wire, PIV, and so on. What's very useful for this work is the so-called pressure neutral wind tunnel, which basically sucks out. We have a mechanism that sucks out air from the bottom and replenishes it from the top, and this essentially prevents the recirculation in the wind tunnel especially for the hover condition, which is known to contaminate the noise measurement. Okay, so moving forward, and like I said, we performed the experiment in this pressure neutral wind tunnel. We have 2 test blades, and we 3D printed them. And these are the description of the blades, and we measure them at different range of velocity and RPM. And here I'm showing again the parity plot, and you see that as we expect, you have very large leading squares error associated with this the low fidelity prediction. So then that's no surprise. So we need to enrich this low-fi DNN with some high fidelity data, and this is what we did. So so we had to generate a high-fi data set, and to that end we looked at 18 different blades with different P over D ratio, different max camber and so on, thickness and so on. And we 3D print them, and we test them at different velocities and different RPMs. And this gave us, and we discarded the windmilling ones. So this gave us about 108 training samples. So a very small set of hi-fi data. And we call that DHF. Okay. So now let's do some. The question is now, how do you reconcile? How do you hybridize the 2 sets of data, low-fi and hi-fi? So the goal is to update the low-fi DNN by including additional hi-fi data, DHF. So as a reminder, the low-fi DNN, you have the weights of WLF. What we did in transfer learning is that we split the DNN parameters into 2 sets. And the first set is WLF1, and the other one, the remainder is W2. So W2 are the weights associated with the last DNN layer, and the WLF1 are the remaining weights. And we freeze the remaining weights, and we only retrain the DNN using for W2 for the last layer using the new high fidelity data. And then once we get the new W2, we augment that with the frozen weights from before, and that gives us a new, now multi-fidelity deep neural network. The advantage of doing it this way is twofold. One is so you've got the source domain, you've got the low-fi DNN. This way, it preserves the trends that you've already learned from the low-fi, but yet still allows you to the trends that are unique to the hi-fi domain to be learned and corrected. And the second one is it prevents overfitting, because in the whole point is to have small amount of hi-fi data. So so by doing transfer learning, it prevents you to some degree over, because this is because the weights associated with the last layer is quite small. Okay, so let's see how this multi-fidelity DNN performs. So we have again 2 blades, 2 test blades. Let's look at the first one. The first one is just you can see it's a NACA 3320 profile with a pitch diameter ratio of 0.9. What you see, so here, blue, low-fi blue, and the experiment in black, and you see that here we are looking at different frequency range at 3 different polar angles, and you see that very significant improvement of the broadband SPL prediction compared to the low-fi model. It actually tracks the experiment, the hi-fi experiment, really well over the entire frequency range. So, and that's just one condition. So if you look at both blades at all operating conditions and at one frequency, and you see, again, here we're showing the parity plot, and you see that the multi-fidelity machine learning model that's trained with both hi-fi and low-fi data using transfer learning can really significantly improve the predictive accuracy. Okay, so the moving squares error, we reduce it by a factor of 4. The interesting that the DNN trained using just high-fidelity data, it does improve the prediction, but actually not as much as the multi-fidelity approach.
Like low fidelity plus high fidelity look better than
correct, and
high fidelity alone.
exactly, and this again goes back to the advantage number one is that the low fidelity allows you to set up a foundation, and then it's corrected by the limited hi-fi. Otherwise, if you use just hi-fi, you don't have enough data. Okay, this basically more or less says the same thing. So the top row, now we're looking at all frequencies. Okay, so top row, low-fi, the middle row, hi-fi only, and then the last row is the multi-fidelity. So again, multi-fidelity by far improves the prediction the most. Looking at different polar angles and different frequencies, and again, and here the different colors are different polar angles, and then different shades are different fidelities. Okay, so low-fi, hi-fi, and the transfer, so mixed fidelity. So again, this really just shows that the transfer learning approach is able to improve the accuracy even more than just hi-fi. And in fact, the transfer learning based DNN outperforms the hi-fi on 18 out of the 21 output quantities of interest. And this work we presented last week also at Aviation. So again, if you're interested, please have a look. And the next step we want to take is a couple of things. So one is to go back to the tonal part and also include the tonal part, which I showed before. And the second thing is to use the active learning, which we have explored in the tonal part, which we did not have a chance to explore for the broadband part. And this will allow us to add new plates intelligently to even further reduce the predictive error. And something else is some other things are to include additional features like other plate counts, angle of attack, and non-constant core distribution, and so on. So I'm about to show some other highlights or so other developments, but I see that I've taken a lot of your time already, so I'm going to go through these real quick. So this is a runs-based, the mid-fidelity runs-based approach to reduce tonal noise. Okay, so I'm going to go through this real quick. This is based on SU2. The deformation is done performed using a radial basis function. This whole thing is in collaboration with Professor Alberto Guardone's group in Polimi in Italy. Just some results. So baseline blade unconstrained noise minimization, thrust constrained noise minimization, and you see that you have very strong, large noise reduction in the unconstrained case. If you don't constrain the aerodynamic performance at all, you get about 12 dB reduction, but you lose almost all the lift. You lose 80% of the thrust, 80% of the thrust, and you have and this is achieved by very strong shape changes and by shifting the load away from the tip. And on the other hand, for thrust constrained case, the changes are more nuanced, more minute, and the noise reduction is more moderate. But it's still something like 3 dB, which is not trivial.
It's not little.
3 dB is not little, especially for such a propeller, because that's it's not a full scale propeller. This work was also presented by Luca Albergo last week at Aviation. So if you want more details, please have a look at that paper. And this is the last slide that actually contains some information. So this is some very recent work that we're doing actually with Max, who's sitting in the audience with us today. It's a time domain method, boundary integral method to account for acoustic scattering. And this goes back to one of my first earlier slides that for UAM type of configuration, scattering is very, very important. So it's you cannot discount that. So essentially, it's a rather new Galerkin-based approach, and this will be coupled with our in-house mid-fidelity solver. It's implemented in Jack, so it allows GPU acceleration. And in the summer, working with Len, Max will be implementing the adjoint solver to allow us to do design optimization against scattering. Yeah, these are just some earlier validation work. One of the case we want to target is the scattering case of a propeller over a semi-infinite plate. Here, the propeller is rather close to the plate, and we're actually going to we can actually move the propeller to the edge, over the edge of the plate, so the edge scattering becomes important. And this was measured in our wind tunnels as well. Okay, so that's it. Presenting some first and low fidelity framework that allow us to do aerodynamic and aeroacoustic optimization, and this is complemented by machine learning enhancement of the broadband noise model. I show some high fidelity results for isolated propeller and multi-fidelity data-driven method to further enhance the prediction, and some, here are also some ongoing development as well. Finally, I just want to acknowledge the talented students who have been working with me, who have done all the work as well, and also our collaborators, in particular, Dr. Nick Zhang, who's with us in the audience today, Professor Azad Peivan, also the folks in Michigan, Stanford, at MIT, and Milano as well. So there are just some related publications, and thank you for your attention, and happy to entertain some questions.
You have to come for much longer and give 5 presentations, not one. So you definitely have enough material.
Is there anybody online with questions? What?
Okay. Okay. Any question from audience?
Okay. So, I'm doing similar work, right? That recent VFS paper, and I found something similar where the optimizer really fattened inboard and shrank outboard, just for efficiency alone. Did that, and it had a acoustic benefit. And I think we have to add scattering, we have to add a million things. We're going to have to add structures pretty soon to push back against that fattening of the board. That's why I want on the boards here today and see, okay, well, because I've got no experience with structures at all, much less design optimization, including structural analysis. Have you guys thought about that at all?
Yes, in fact, we actually recently submitted a big European proposal on aerodynamic, aeroacoustic, and aeroelastic optimization of isolated propellers. It's the whole framework. If you want to set it up properly, it's not trivial, because you have to iterate between if you do an adjoint-based approach, you have to iterate between all 3 parts. And I will also add that the structural deformation in many load cases is not steady, right? The blade flutters, and so I'm not sure if you have a steady deformation, it accurately captures the things. Perhaps Nick will have more insight because he actually did a lot of the experiments.
On the rubber, it's spent all the way to the way. So much longer than the usual propeller we test. I mean, we can't really ask why, But there must be some structural reasons that they do not so-called reduce the code so much for the TV.
Well, certainly aerodynamic benefits, right?
There is, yeah.
So they,
But it's really loud.
yeah, well, they're not thinking like this. I mean, there's so much to add to these things. I think we have to also think about multi-point. You know, design a blade for hover and for forward flight, of course. You know, 2 different RPMs. Is it pitch controlled? Or is it RPM controlled only? Or both?
Forward and hover.
Yeah,
Forward and hover,
combine them
yeah,
into
yeah,
one
yeah,
objective.
Yeah.
Yeah, there's just so much to think about.
Also, you can design the blade to the shape to work for, let's say, hover and also different, flight velocity, different advanced ratios. But also
Blade actuation, so that the blade.
yeah, so
change
you
shape
can also
in
well,
flight.
no. So the, so the shapes are the blade shapes are fixed, but you can also
RPM definitely we can change.
you can change it. But also the collective
RPM angles.
the collective you can also
That
change,
all
right?
can be changed.
Yeah.
I don't think it's actuated. I don't think you can do like collect cyclic.
Oh, yeah.
Collective.
Hey,
Collective
any
you can
kinematic parameters you can change.
Yeah.
But you cannot change shape, I see.
The shape you cannot change.
The more physics we add to these problems, I mean, the more dimensions, this is gonna be getting really, really fast.
Yeah.
Really fast.
No, it's really good. You know, it's a lot of area for research.
Yeah, and like, I think we also have to do for these vehicles, do things like an integrated, like, I know you did different mics, which is good, right? But I think you also need to do something like, for forward flight, just have a bunch of angles that you can then, as things fly over, you can do an integrated method, like an SCL or something like that. And that's an easy way to say, okay, I've got one number, maybe I'm doing an in-plane, but then I'm changing the directivity, or if I'm scattering, certainly I can just avoid the lobes and, oh, it's quieter, but you move a little bit. But if you do kind of an integrated approach, you kind of wash all that out to one thing. And we may find that when you integrate like that, the noise doesn't really, you don't get 3 dB, you get half a dB or, something much smaller when you integrate all these things together.
And we should, not a small point, but we should validate the optimization. In the sense that, like,
that's what you're doing, that's what we're doing, right?
yeah. So
You need to design and then actually to test it.
you actually
What
test
you
it.
design, you actually get an actual.
Yeah, but so again, I won't point we're doing something very similar to you, where we design something and then test it.
Yeah.
So we did a broadband noise using Berkeley Marcolini, and we're planning on testing it this winter to see if we're even close. Tonal noise, just like you guys, we nailed, but broadband noise, that's a whole different beast. Good. Yeah.
You are not missing your plane? Or?
And no, I just need to leave by, let's say like 11:30. So
Okay.
I've got
Okay.
it.
Okay. Otherwise, you can make 5 other presentations, right?
Okay. Any more questions?
Any other question?
Thank you very much. Thank you.
Thank you.
Who do I contact again?